All right, hi guys. This is chapter 16, solve problems. I've taken a problem from the book and I've changed the figures around a little bit just to make them match up with your problem this week a little bit better. Also, so that we get a modification at the end, which is important for you guys to see. This is what's called a job assignment problem, specifically the Hungarian method. You'll see in the book that term. The idea is who should be assigned what, or what should be assigned where, by using a method of reducing every row and column by a certain number until you arrive at an optimal solution. This is the kind of problem you could set up as a linear programming problem. That's the kind of stuff you'll do when you get to quantitative methods if you haven't done that class already. We're setting this up, like I said, with the assignment method or the Hungarian method. And we're going to do two versions of this problem. One version where we're looking at costs. That's the typical problem. And then we're going to do it again and do it with profits. Profits is a little bit, spoilers, profits is done a little bit differently. So we're going to go through it twice. And like I said, I've changed the numbers around just so that we arrive at a different solution, which requires a modification at the end. So let's get started and take a look at it. I've got very explicit instructions on the left side of the screen, but you'll still want to review in your book and double check it before you submit and you do each part of this. You will have a question about this on quiz, exam. You'll have to do the same thing by hand. Fortunately, it's very easy to do by hand. You just need a sheet of paper, pen and paper, and it's not difficult to do by hand. For this work, you'll want to show your work, so you have to use Excel formulas to show your work and how you've actually solved it. But when you're solving it for purposes of your quiz or exam, like I said, the method's actually pretty simple to do by hand, not terribly challenging. You'll be asked, what job should be assigned to what, so you'll have to go through it. Takes a little bit of time, but not dreadfully difficult compared to some of the other things we do in Excel that aren't as easy to do by hand. So what's going on here? You've got three jobs, and each job needs to be assigned to one of three machines. This might very well be an employee assigned to a job or a person assigned to a task. It can just be any kind of this assigned to this situation during scheduling. But in this case, if the machine does this job, it's going to cost $16. If this machine does this job, it costs 10. This job, it costs 9. So the idea is that some people are better suited for certain tasks, or some machines do certain jobs better, maybe more efficiently. Maybe they're located in a certain spot, and so there's better costs associated that we can try to figure out to do the least costly method of having all the jobs and machines assigned to one another. So the first thing we do is we reduce each row by the lowest number in each row. And what I mean by that is the lowest number in this row is 10. So what we're going to do here is reduce every number in this row by 10, and we're going to write it in the row reduction section down here. So if you're doing this by hand, you would look at 16 minus 10, 14 minus 10, and then 10 minus 10. And by hand, you would just write down 16 minus 10 is 6, 14 minus 10 is 4, 10 minus 10 is 0. Okay, the lowest number is 10. You're subtracting that from every row. But for purposes of this class and this problem set, they wouldn't be showing your work. So what we're going to do is we're going to take the current number that we're on, whatever current number that matches. So this 1A section, this matches. And then we're going to subtract from it the smallest number in this row. If I lock that in, I get 16 minus 10 is 6. And if I drag this over, 14 minus 10 is 4, 10 minus 10 is 0. So it works. Then I just do that again. So equals this minus the minimum of each row, minimum of this row, lock it in. And when you do this, it's pretty easy to see the math. So double check that you didn't make a mistake in your formula. The lowest number is 8. So 10 minus 8 is 2, 13 minus 8 is 5, 8 minus 8 is 0. Okay, then the formula worked. So just double check yourself as you go. This number minus the min of this row. 9 minus 9 is 0, 9 minus 9 is 0, 11 minus 9 is 2. So far so good. We've reduced each of these numbers in this row by the lowest number, okay? That's step one. Step two is to subtract the lowest number in each column from the lowest number in each row. So often you'll find that the lowest number in each column is now 0 and you don't reduce it by anything. And when that happens, you have to do another step at the end. But sometimes that isn't the case. Sometimes, you know, if all this would have to be is 8, and now the lowest number of this column isn't 0, and it's a little bit different of a story. But for the sake of this problem, I'm setting it up to where we need to modify at the end. So if you're doing this problem by hand, you don't need to do this step at all, because the lowest number in each column is 0. So when you subtract the lowest number in each column, you'll know that it's not going to change at all. You can skip right to the modification step. Again, only if you're doing this by hand, okay? So the lowest number in each column is 0. So I'm still going to go through the same formula to show my work, which is this number minus the lowest number in this column. So straight up and down instead of side to side. Lock it in. And now 6 minus 0 is 6, right? They match. Do that again. This number minus the min of this row. Copy it down. And then one more time. This number minus the min of this column. And copy it down. So again, it didn't change. If you're doing this by hand for your quiz, your exam, just skip it. If they're all zeros, save yourself the time. But for the problem set, you got to show your work. So now after the column reduction, sometimes it's just as simple as 2 steps: row reduction, column reduction, okay? However, we're checking for optimality. And how we tell optimality is we figure out the fewest number of lines that I can draw and cover up every 0. Okay, so right here, if I drew one line here, I've covered up 2 zeros, and if I drew one line here, I would cover up those zeros. Okay, so a couple ways you could do this to show your work. I'm fine if you just want to highlight the as if there were lines. That's fine. It's easy to see. You could also, what I typically have done in past classes, although it's a little more time consuming, is to have you go in and go to the shape section and then find lines. It's under insert and then illustrations and then shapes, and find a line and draw it. I'm okay with the shading though. It's easier to do and see. So if you wanted to shade those, it's fine. I would use a different, gray or maybe something. There we go. So that's where the minimum number of lines that I can draw to cover up all the zeros. And what I'm looking for is the fewest number of lines that I could draw and cover up all the zeros equal to the number of rows or columns. All right. The number of rows is 3. There's 3 rows here, 3 columns as well. And if the minimum number of lines that I could draw and cover all the zeros is also 3, then I'm good. Optimality exists and I can make an assignment. However, I can do it in 2, which means we have not reached an optimality. The minimum number of lines has to be equal to the number of rows or columns in order for us to have reached optimality. It's not the case here. So what we do is look to the intersection of these lines. So the intersection of these lines is right here at C3. And I'm going to shade that a different color just for purposes of identifying it. And now I'm going to subtract that number from all the unshaded numbers. So 6 minus 2, 2 minus 2, 4 minus 2, 5 minus 2. And I'm going to copy that down to here. So to show my work here, you could do, equals, oh, you know what? Sorry, that's not the case. I said that whole thing wrong. I don't want to restart the recording though. The numbers happen to be identical, so it confused me. You reduce each of the unshaded numbers by the lowest unshaded number. And then whatever that number is, you add to the intersection. So strike that last part from the record. The unshaded parts are these numbers. The smallest of these is 2. So I'm going to subtract 2 from each of these numbers. So 6 minus 2, 2 minus 2, 4 minus 2, 5 minus 2. And whatever number it is I subtracted, I'm going to add to the intersection number. So this 2 becomes 4. 2 plus 2 is 4. So for that reason, I can do equals this number minus the lowest of all 4 of these unshaded spots. And I can copy that over once. I can copy that down once, as long as I locked it in, right? 6 minus 2 is 4. 4 minus 2 is 2. 2 minus 2 is 0. 5 minus 2 is 3. And everything else just is equal to what it was. So equals that, equals, we can just maybe copy this down. Doesn't quite work. You know what, for this bar, you can just type the shaded lines in. This number is going to be equal to this plus the min of this though. So we took all the unshaded, anything without a line over it, and we subtracted the lowest of those numbers from themselves. 2 was the lowest number, so all of these were minus 2. This was the intersection of the lines previously, so we add 2 to that number. It becomes 4. Now let's draw lines again. And if I was to draw a line here, here, and here, I could do it in 3, okay? So I could do it in 3 there, or I could do it, here, I'll do it a different way. I could do it this way, there's 3, or I could do it 1, 2, 3. What I can't do is I can't do it in 2. So the minimum number of lines that I need to draw to cover up all the zeros is now 3. The number of rows is 3. So now I know that optimality does exist. If not, you have to keep doing it until you've reached optimality, but you should find it at this point. So I found optimality. Let's show my lines again, and I'm just going to, maybe do 3 different colors to throw just 3 different lines. That might be better. I'll just throw 3 different colors at it. There's 3 different lines. That works. Okay, so 3 different lines to cover it up. That was the requirement. And now we can make our assignment. So how do we actually make our assignment? We look at everywhere we look to see if there's only one option in a row first. And the lowest the cost here, the better. So what I'm going to do is I'm going to look at row 1, row 2, and row 3, and I'm going to look for, this color shading. So not as easy to see. I'm going to go and draw the lines just to make it easier for you guys to see the colors behind it. There's 1, there's 2, there's 3. All right. So I look in this row and I see, is there more than one option with 0? And there's not. There's only one option there. There's 2 options here, and there's 2 options here. So I'm going to start by making my assignment 1C based on there only being one good option in this row. So I'm assigning 1 to C. And here on 1, I'm going to say equals C. And then I'm going to look and see what the actual cost is. And the actual cost where 1C is 10. So 1C is the assignment here, and that's 10. Now I'm going to look back down here, and we have to think this through, because if 1 has been assigned and C has been assigned, right, then none of these are our options anymore. So now I look at the remaining rows, and on row 2, I have option A or B, 0 and 3, and on row 3, I've only got option A or B left, right? C's been assigned at this point. So now I look at these 2 options, I say 0, 3, okay, well, there's only one option here, which is A, that is worth 0 points. So I can't choose either one. If they were both zeros, if they're all zeros now, I could say, well, 2 can go to A or 2 can go to B, and it's irrelevant. However, there's only one optimal assignment now, and that's 2 to A. So I'm going to assign 2 to A, and that's going to equal $10 here. And then 3 is going to be B, because that's the only thing left over, right? A and C have been assigned, so the only thing left is B. And where 3B is cost meets, that's right here, $9. So that would just be the sum of these costs, $29. So you can play around and see if there's any cheaper way of doing it, and there's not. And you can kind of, when you understand this part of it, you could look at the original problem and kind of work through it to figure out what the likely assignment is going to be. Right, this is so much higher that you almost have to assign 1C, otherwise it's $4 more to assign to B and $6 more for A. So this seems like it's probably going to be it right there. But then you got to look and see if this is assigned, how much more is this than that? Only $2 more. How much more is this than that? It's not. So 3 is going to be A or B no matter what, right? So if 3 is A or B no matter what, then 2 would rather be A than B because it's $3 cheaper. I mean, it'd rather be C, but this is $4 cheaper. So, you know, it once you've done this a few times, you can kind of eyeball that and say, oh, it's going to be 1C, 2A, 3B. Nothing else really makes sense for how big the disparity is in some of those costs. So again, when you're doing this on your quiz or on your exam, which you will, very similar process, a little bit faster probably, because it's simple math, right? 10 minus 8 is simple math. He's right that you should, I mean, I'm not gonna say you should be able to, but you likely could eyeball that and say that 13 minus 8 is 5 and write down 5 without having to do a whole formula. But you know, you've got plenty of time in the exam, so I would use my calculator anyway, just to double check. All right, let's look at how you do it if it was profits and not costs. So when you do it and it's profits and not costs, you have to relativize the numbers first. And what that means is that you effectively are going to take, you're going to make each of these the inverse of themselves to see if this was my profit, if I assigned 1 to B, I'm going to switch it and say, try to figure out how much profit I would be losing by picking that versus picking something else. And what that's going to do is I subtract each number from the largest number in the entire table. So in this case, the largest number of this entire table is 9. So I'm going to take each of these numbers and I'm going to take 9 minus that, and I'm relativizing it to the highest profit I can. So if I could make $9 profit here, then I'm making 4 less profit by choosing 1A here. I'm making 2 less profit if I choose this. I'm making 3 less profit. And so that profit becomes a relative cost by comparison. So this one's pretty easy to do the relativization. And I take the maximum, the highest number in this entire table, lock it in, and then I subtract my current cell from that. So 9 is the maximum, the highest number in all that, and 5 is my current cell. So 9 minus 5 is 4, 9 minus 8 is 1, 9 minus 6 is 3. So I should see 1 and 3 when I copy this over, and I do. And then once I copy it over, I can copy it down. And so now I've relativized the table. So this is the relative cost based on how much profit I could make. If I choose 2C, I make $9 profit. So if I choose 2C, I have not missed out on any profit. Thus, I have not caused myself any kind of relative costs. All right. And then once you do that, the problem is identical to the previous problem. There's just the added step when you're comparing profit, when you have a profit table, of relativizing it first. And then you launch right into row reduction, and then you go into column reduction. So let's do it one more time so you can see that process. And I just want to point out modification only if needed. If you are doing your problem set and you get to the column reduction and maybe it's 3 rows and the minimum number of lines is 3, you do not have to do this step. You can just leave it blank. This is modifications only if needed. And I'm not going to tell you if it's needed or not. Might be. So row reduction. So let's subtract the lowest number in each row from each number. So 4 minus the lowest number in this row. And I actually can lock in the column only, then I can shift the rows. So you can do that by not covering up the rows. So if I won't lock in row 10, and I should be able to actually use this for the entire thing now. Yeah, 3 minus 0 is 3, 2 minus 0 is 2, 5 minus 4 is 1, 4 minus 4 is 0, 6 minus 4 is 2. So that worked out. So the difference there was that I only locked in the column E. I wanted E to stay the same, but then I wanted E to copy down to row 11 and row 12, and it did. So when you lock in the cells, you can keep pressing F4 until you cycle through those different options. The base, the default when you do that is you have $signs before the column and the row, but you don't have to lock in both. All right, so we've done that, and now we're going to subtract the lowest number in each row from each number in each row. Okay. So as you will see here, there's zeros in this row or column, zeros in this column. And I think I said row on accident, but we're subtracting the lowest number in each column from each one. And there's a 1 here. So because there's a 1 here, we know we're going to subtract 1 from each of these, whereas these ones have zeros, so we're not going to subtract anything. So again, if you're doing this by hand, you could just scratch this out and put a 2, scratch this out and put a 2, scratch this out and put a 0, and then work off of that. You don't necessarily have to write 4 different tables on your paper. Just some tips on how you might accomplish that for quiz and exam purposes. All right, so let's do each number in the row minus the lowest, I said row again, in each column minus the lowest number in this column. And now because I'm copying this way, I want the row to stay the same, but I want the column to shift. So the minimum of this one, I want to have the row locked in, row 16, 17, and 18 locked in, but I want the column to shift from E to F to G. Let's see if that works. Copy down and then across. Yeah, that worked. So 3 minus 1 is 2, 3 minus 1 is 2, 1 minus 1 is 0. Those all stay the same. And now check to see if there's optimality, if there's an optimum assignment to be made. So I'm just going to draw it this way, and I'm going to say, can I do it in 2? 1, 2, no, I take 3 that way. 1, 2, no, it takes 3 that way. 1, 2, 3. So no, it's going to take 3 regardless, it looks like. So that means that we don't need to modify. So I'm going to go back and draw my lines. Like I said, if you want to do 3 different colors of highlight here, that's fine. I'm just going to draw these. Either way. Those are done. And then we know an optimality exists. So let's look at each row. And I'm going to say there's only one option here, right? Because there's only 1, 0, 1, 0. So I can actually highlight those here. And now 1's covered, 2's covered, 3's not covered, B's covered, C's covered. So that only leaves 3A left over. So what are my profits? We're going to have 1B, 2 is C, and 3 is A. And my profits here are going to be based on the original formula here. So 1B is 8, 2C is 9, 3A is 4, which I really should do equals that, equals that, equals that. And then here's going to be my equal sum of this column. $21 profit. And I don't think we'll find a better profit. 9's pretty high. If I went to here, then the best I could do here is 6. So even if I got this 5 here, it would cost me money. That'd be 19. So yeah, 21 is the highest profit with that configuration. So that works. All right. So that is the job assignment problem using the Hungarian method, row reduction, column reduction, and then modification if needed. Please feel free to ask questions.